Welcome to Ask and Learn.
By a force of 500 newtons and at a 45-degree angle. And on the right side of the crate, it's being pushed with a 400 Newton force at a 35-degree angle. And while this crate is being pushed, it's also experiencing friction, and in this case, kinetic friction. So we're given the coefficient of kinetic friction is 0.2. Also given the mass of this crate, which is 100 kilograms. And so before the box is being pushed, it's at rest. And we want to find the distance after it reaches a velocity, which we'll call v2 of 8 meters per second. So we want to find, again, some distance s. So because we want to find a distance and we're given forces, we know that there's some work involved. And because we're given velocity, we can use what's called the work energy principle. And that's given as the initial kinetic energy plus the work being done is equal to the final kinetic energy. And of course, we can expand this to 1/2 the mass times the velocity squared, in this case v1, the initial velocity, plus the work being done, and that's the force, and in this case it's in the x direction, times s, the distance. S is what we're looking for, is equal to 1/2 m v2 squared. And so again, the object or the crate is at rest, so this part of the equation goes to 0 because the velocity at rest, of course, is 0. So that makes our equation much easier. So we have f of x times the distance is equal to 1/2 mv2 squared. So looking at this equation, we know, which we'll call equation 1, we know the mass of the crate, we know its velocity, which is 8 meters per second. What we're looking for is s, the distance, but what we don't know is the combined force in the x direction. So to do that, we first have to create a free body diagram to show all the forces, and that way we'll be able to find the combined forces in the x direction. And this is where it gets a little complicated if we're not careful in designating where the forces are at. So we know that the crate has a weight pointing straight down, which is given as just mg. So that means there's a force in the opposite direction, Fn. So let's look now at the right side. There's a force being pushed at some angle, which is 400 newtons. So we can break this into components. So we have a force in the y direction pointing down, and we have a force in the x direction, which is, the motion is going to the left, so the force f of x is to the left. And so from this triangle, we know from geometry, f of x is equal to f cosine theta. Theta is right here, and we know theta is 30, in this case 30 degrees. So f of x is 400 cosine 30 degrees, and we know then f of y is equal to 400 sine 30 degrees. Okay, now on the left side we have another triangle at a 45-degree angle, and of course we can break this down into components as well. So the motion's to the left, so we know that f of x for this triangle is to the left, and so the force in the y direction is pointing up. And of course this force is 500 newtons. So this triangle on the left side you know that f of x is again f cosine theta, and f here is 500, so we have f of x is equal to 500 cosine 45 degrees, and then f of y is 500 sine 45 degrees. So of course we want to find the combined forces in the x direction. So let's look at the x direction. So if we say the force is to the left and the force is pointing up, or the positive direction, looking at this diagram, we have this f of x and this f of x pointing to the positive direction left, but we also have friction, and friction is always in the opposite direction of the motion. So we have friction that way, which we'll call f of k, because force due to kinetic friction. So then our equation in the x direction becomes the two f of x's. So you have 500, we'll do 500 cosine 45, so from the left side, plus the right side, so 400 cosine 30 minus the force due to friction, which is given as mu k, the coefficient of kinetic friction, times f of n. So we're given mu k, what we're not given is f of n. Looking back at the diagram, f of n is in the y direction, so now we have to go find the forces in the y direction, solve for f of n to plug back in to our equation for the x direction. So y direction, so we have f of y's on both sides, and we have f of n pointing up and mg pointing down. So again, so we have positive f of n on the left side, we have a positive f of y, and on the right side we have a negative f of y, and then mg, the weight, is also negative. So we say, okay, f of n is positive plus the force on the left side, which is 500 sine of 45, and that's positive because it's pointing up, minus the force on the right side, and that's pointing down, so it's a negative 400 sine of 30, and then the weight is pointing down as well, so that's a negative, and the weight is just mg, so we can plug in those numbers. So m is 100 times gravity, 9.8, and all these forces balance each other out, so that's equal to 0. So if you plug all this in, move it to the right side to solve for f of n, we have f of n is equal to 826.45 newtons. And now we can plug this in back into the forces in the x direction. So we have 500 cosine 45 degrees plus the 400 cosine 30 minus the number we just found. Oh, well, it's the, going back to it, it's the kinetic friction, coefficient of kinetic friction times the normal force, which we just found, so it's 0.2 times 826.45. So then the combined forces in the x direction is found as 534.67 newtons. So now this number we can plug back in to the equation right here, equation 1. So equation 1 now becomes 534.67 times s, the distance, which is what we're looking for, is equal to 1/2 the mass 100 times velocity, which is given as 8 squared. So now we can just solve for s by dividing both sides by 534.67. So s, the distance, is found as 5.98 meters.